Hello! In this video, we are going to prove the following theorem. Let xn be a sequence of non-zero real numbers, and suppose the limit as n approaches infinity of absolute value of xn plus 1 over xn converges to a value less than 1. Then, the infinite series from I equals 1 to infinity of xi converges. Okay, now to start out the proof, since L is less than 1, we can pick some real number R between L and 1. Now, since every term in this sequence is greater than 0, well then, the limit of this sequence must be greater than or equal to 0, right? If you recall, that's one of the properties of limits. So L is greater than or equal to 0. Since L is greater than or equal to 0, this tells us that R lies between 0 and 1. Right? This is going to be important throughout the rest of our proof. Now, since this sequence converges to L, well, by definition of convergence, what does that mean? Well, it means the following. It means for every epsilon greater than 0, there exists a positive integer capital N, such that for all n greater than or equal to capital N, the absolute value of xn plus 1 over xn minus L is less than epsilon. Now, we know that this sequence converges to L, which means we are given that this statement is true. And this statement works for every positive real number. So in particular, it must work for the positive real number R minus L. So taking epsilon to be R minus L, we have that this statement is true. So there exists a positive integer capital N, such that for all n greater than or equal to capital N, the absolute value of xn plus 1 over xn minus L is less than R minus L. And I can call capital N whatever I like, so I'm going to call it capital N1. So notice, if we give ourselves any integer n greater than or equal to capital N1, we know that this inequality is true. But also, clearly, this inequality is true because every real number is less than or equal to its absolute value, and we know that this guy is less than R minus L. So this guy is strictly less than R minus L. So if we take this strict inequality and add L on both sides, the L's will go away. And we have that absolute value of xn plus 1 over xn is less than R. Now, we can re-express this inequality because we know that absolute value of xn plus 1 over xn is equal to absolute value of xn plus 1 over absolute value of xn. So we have this, but then if we just multiply absolute value of xn to the other side, we get this. So given any integer n greater than or equal to capital N1, we have that this inequality is true. So as you can imagine, if we give ourselves any integer n greater than or equal to capital N1, this is true. Right? But if we multiply both sides of this inequality by r, well, since r is greater than 0, the sign of the inequality will remain the same. So we get this. But then, since n is greater than or equal to capital N1, certainly n plus 1 is greater than or equal to capital N1. So, since this statement works for every integer greater than or equal to capital N1, then in particular, it must work for n plus 1. So taking n to be n plus 1, we have that absolute value of xn plus 2 is less than r times absolute value of xn plus 1. So notice the pattern that's going on here. Absolute value of xn plus 1 is less than r to the power of 1 absolute value of xn. Then absolute value of xn plus 2 is less than r squared absolute value of xn. In general, we should expect absolute value of n plus k to be less than r to the k absolute value of xn for any integer n greater than or equal to capital N1 and for any positive integer k. And so we're going to show that this is true by induction. So, to prove this, let's give ourselves an arbitrary integer n greater than or equal to capital N1. And we're going to proceed by induction on k to show for all positive integers k, this inequality is true. So let's start with the base case. In the base case, we're dealing with k equals 1, and we're trying to show that this inequality is true in the case where k is equal to 1. Now, we know that this statement is true for all integers n greater than or equal to capital N1. For reference, let me label this statement star. Since this statement works for every integer greater than or equal to capital N1, then in particular, it must work for the integer n that we introduced right here. So we have that this statement is true for the n we introduced here. Of course, r is equal to r to the power of 1, and so this inequality is true. But this is precisely this inequality in the case where k is equal to 1. So this completes the base case. Now, let's move on to the induction step. In the induction step, we give ourselves an arbitrary positive integer k, and we assume that this inequality holds. The whole goal of the induction step at this point is to show that this inequality is also true, where instead of k, we have k plus 1. Now, we're going to apply statement star again. But now we're going to take n to be n plus k. So, taking n to be n plus k, we get absolute value of x n plus k plus 1 is less than r absolute value of x n plus k. But then, let's remind ourselves, by the induction hypothesis, this inequality is true. And since r is greater than 0, if we multiply r on both sides of this inequality, the sign of the inequality will remain the same. We're going to get r absolute value of xn plus k is less than r to the k plus 1 absolute value of xn. And so this shows us that this guy is less than this guy. That's precisely this inequality where k is replaced with k plus 1. So this completes the induction step. Because we've completed both the base case and the induction step, this closes the induction, and so we have proven that this statement is true for all integers n greater than or equal to capital N1 and for all positive integers k. And so I'm going to call this statement star star. So we've proved star star. So now we're going to move back up to the top because we're going to be moving into the next important part of the proof. For the next part of the proof, we're going to prove that the limit of the sequence xn is equal to 0. How do we prove this? Well, let's go back to the definition of convergence. By definition of the limit of a sequence, this means the following. To say that the limit of the sequence equals 0 means for every epsilon greater than 0, there exists a positive integer capital N, such that for all n greater than or equal to capital N, the absolute value of xn minus 0 is less than epsilon. So, since we're trying to prove a state about every epsilon greater than 0, let's give ourselves an arbitrary epsilon greater than 0. From here, we want to find a positive integer that makes this statement true. Since r lies between 0 and 1, well, if we recall, the limit of r to the n will be equal to 0. So then, by definition of convergence, what does this mean? Well, by the definition of limit of a sequence, this means the following. It means for every epsilon greater than 0, there exists a positive integer, capital N, such that for all n greater than or equal to capital N, the absolute value of r to the n minus 0 is less than epsilon. Now, this statement works for every positive real number. So in particular, it must work for the positive real number epsilon over the absolute value of x and 1. Right? We know that this is a sequence of non-zero real numbers. So if we consider the sequence of absolute values, well, that's a sequence of positive real numbers. But certainly, absolute value of x and 1 is positive. So yeah, epsilon over absolute value of x and 1 is positive. So taking epsilon to be this quantity, we have that this statement is true. So there exists a positive integer I'll call capital N2, such that for all n greater than or equal to capital N2, the absolute value of r to the n minus 0 is less than epsilon over absolute value of x and 1. Now remember, the whole goal is then to show that xn converges to 0. Remember, we're in the process of proving this statement. At this point, we gave ourselves an arbitrary epsilon greater than 0, right here. And now we want to find a positive integer that makes this statement turn out true. Well, the claim is that the positive integer n1 plus n2 will make this statement turn out true. So taking capital N to be capital N1 plus capital N2, we proceed to show that this statement is true. Well, since we're trying to prove a statement about every integer greater than or equal to capital N1 plus capital N2, let's give ourselves an arbitrary integer greater than or equal to capital N1 plus capital N2. I'll call it n. And our whole goal from here is to prove this inequality. Now, since n is greater than or equal to capital N1 plus capital N2, this means we can write n in the form capital N1 plus capital N2 plus p for some integer p greater than or equal to 0. In fact, p would just be equal to n minus capital N1 minus capital N2. But we're just going to write this. But now that we have that, we're actually going to apply star star. In applying star star, we're going to take n to be capital N1, and we're going to take k to be capital N2 plus p. With these two choices, we get that absolute value of x capital N1 plus capital N2 plus p is less than r to the power of capital N2 plus p times absolute value of x capital N1. And remember, capital N1 plus capital N2 plus p is equal to n. So this is just absolute value of xn. And absolute value of xn is just absolute value of xn minus 0. The reason why I'm writing this is because we're in the process of proving this inequality. So I'm writing the left-hand side of the inequality right here. But then, let's remind ourselves that this statement is true. And this statement works for every integer greater than or equal to capital N2. So in particular, it must work for capital N2 plus p. So taking n to be capital N2 plus p, we have that absolute value of r to the power of capital N2 plus p minus 0 is less than epsilon over absolute value of x capital N1. But of course, this is just equal to r to the power of capital N2 plus p. So we get that r to the power of capital N2 plus p is less than epsilon over absolute value of x capital N1. And therefore, if we take this inequality and multiply absolute value of x capital N1 on both sides, we get that r to the power of capital N2 plus p times absolute value of x capital N1 is less than epsilon. And so, absolute value of xn minus 0 is less than this guy, which is less than epsilon. And that is exactly what we wanted to show. So, we have proven this statement. which proves that this sequence converges to 0. And so now we're going to move back to the top, because now we're going to move into the next important part of the proof, which is proving that this infinite series actually converges. So next, we're going to show that this infinite series converges. Now, what does it mean for an infinite series to converge? Well, by definition, it means that the limit of the sequence of partial sums converges. So we want to show that this sequence of partial sums has a limit. Well, to do that, what we can do is we can prove that this sequence is a Cauchy sequence. Because if you recall, given any sequence of real numbers, that sequence is a convergence sequence if and only if it's a Cauchy sequence. So we're just going to show that this sequence is a Cauchy sequence. That will imply that the sequence converges, which means that the infinite series converges. Now, what does it mean for this sequence to be a Cauchy sequence? Well, by definition, it means the following. This is the definition we're using. It means for every epsilon greater than 0, there exists a positive integer capital N, such that for all n greater than or equal to capital N, and for all positive integers k, we have that the absolute value of the sum from I equals 1 to n plus k of xi minus the sum from I equals 1 to n of xi is less than epsilon. So, to prove that this sequence is a Cauchy sequence, all we got to do is prove this statement. And since we're trying to prove a statement about every epsilon greater than 0, let's give ourselves an arbitrary epsilon greater than 0. From here, we want to find a positive integer such that this statement is true. Now, since we know that this sequence converges to 0, well, what does that mean? Well, let me write it out again. It means this. And we know that this statement is true because we just proved that this sequence converges to 0. And since this statement is true, well, we know that this statement works for every positive real number. So in particular, it must work for the positive real number epsilon. So epsilon times 1 minus r. Because, of course, 1 minus r is a positive number because we know r lies between 0 and 1. So this statement must work for epsilon times 1 minus r. So taking epsilon to be epsilon times 1 minus r, we have that this statement is true. So there exists a positive integer I'll call capital N3, such that for all n greater than or equal to capital N3, the absolute value of xn minus 0 is less than epsilon times 1 minus r. Remember, the whole goal has been to find a positive integer such that this statement is true. Well, the claim is that if we take this positive integer to be the maximum of capital N1 and capital N3, then this statement will turn out true. So let's define capital N to be the maximum of capital N1 and capital N3. From here, we proceed to show, with this choice of capital N, that this statement is true. And since we're trying to prove a statement about every integer greater than or equal to capital N and every positive integer k, let's give ourselves an arbitrary integer n greater than or equal to capital N and an arbitrary positive integer k. From here, let's show that this inequality is true. And let's start out by writing the left-hand side. Now, as you can imagine, the first n terms of this sum is precisely this, right? So if we're subtracting this guy minus this guy, we're essentially taking away the first n terms of this sum. and we're left with the sum from I equals n plus 1 to n plus k of xi. Right, so just like that. But then we can apply the triangle inequality, which tells us that the absolute value of a sum is less than or equal to the sum of absolute values. So this is what we get. But now, it turns out, if we consider an arbitrary term of the sum, we can show that it's strictly less than something else. So let's consider an arbitrary integer I between n plus 1 and n plus k. And now, let's apply star star. What we're going to do is we're going to take n to be the n we have here, and we're going to take k to be I minus n. And these are valid choices. The reason why n is greater than or equal to capital N1 is because n is greater than or equal to capital N, which is greater than or equal to capital N1. The reason why I minus n is a positive integer is because I is greater than or equal to n plus 1, which is strictly greater than n. So really, the reason why I minus n is a positive integer is because I is strictly bigger than n. So with these two substitutions, we get absolute value of xn plus I minus n is less than r to the power of I minus n, absolute value of xn. And this is just absolute value of xi. So we get that absolute value of xi is less than r to the power of I minus n, absolute value of xn. So what this tells us is that given any term in this sum, well, that term must be less than r to the I minus n, absolute value of xn. And therefore, the sum of all of these guys must be strictly less than the sum of all of these guys. So this is what we get. But now, since absolute value of xn doesn't depend on the index of the sum, we can pull it to the outside. And next, let's actually decrease both the lower number and upper number by n. Right? We can do that. The only thing we have to remember when doing this is that we have to increase everywhere we see our index by the amount we decreased it by. So we're going to increase everywhere we see an I by n. So essentially, I becomes I plus n. So this is what we have, but this is just r to the power of I. So this is what we get. But we actually know what this sum is. If you recall, this is just a geometric series. And if you recall, the formula for geometric series is as follows. So this guy is just equal to this. Therefore, this guy is just going to be this minus r to the power of 0. Right? You're essentially just taking the sum, taking the I equals 0th term away. Well, r to the power of 0 is just 1, so this guy is just this guy minus 1. But then we can combine these two guys together into a single fraction. So we get this, and then in the numerator, we can factor out an r. So we get this, but then the claim is, if we remove r and 1 minus r to the k, well, that's only going to make this thing bigger. So why does that happen? Well, the reason why is because r is between 0 and 1, and 1 minus r to the k is between 0 and 1. Right? The reason why, so r is between 0 and 1, well, when we take any number between 0 and 1 and multiply it by itself over and over again, it's still going to be between 0 and 1. So r to the k lies between 0 and 1. But then, if you just negate both sides and add 1, you're going to get that 1 minus r to the k also lies between 0 and 1. So yeah, both r and 1 minus r to the k both lie between 0 and 1. Well, the product of both of them must therefore also lie between 0 and 1. So, since this quantity lies between 0 and 1, it's only making this quantity smaller when we multiply it. So, if we remove it, we've made it bigger. Right? And so that's the idea. So, this is where we're currently at. But remember, n is greater than or equal to capital N, and capital N is greater than or equal to capital N3. So n is greater than or equal to capital N3. Because n is greater than or equal to capital N3, well, let's remind ourselves this statement works for every integer greater than or equal to capital N3. So in particular, it must work for the n we have here. So taking n to be the n we have here, we have that this inequality is true. Absolute value of xn minus 0 is just absolute value of xn. So we have that absolute value of xn is less than epsilon times 1 minus r. Since this inequality is true, it follows that absolute value of xn over 1 minus r is less than epsilon times 1 minus r over 1 minus r, which is equal to epsilon. And so we have shown that this guy is less than epsilon, which is exactly what we wanted to show. And that proves this statement, which means we have proven this sequence is Cauchy. And because we've shown this sequence is Cauchy, this means that this sequence is convergent. Well, to say that this sequence of partial sums is convergent is what it means for this infinite series to converge. And so this completes the proof. And so yeah, that's pretty much it for this video.